The question?
Okay. Talk today, we have the always entertaining Michael Turner, who is going to tell us about looking beyond lambda CDF to solve the
Okay, so this is largely just an expansion upon my comment at the end of yesterday that we ought to aspire for more than lambda CDM, and then it'll go beyond that and say how we should get something more than lambda CDM. So I won't review the checkered history of lambda, but it's about 100 years old, and maybe we should be surprised. I bet Lemaitre and Einstein would be surprised. In fact, maybe they're communicating with me. That this model should be so successful. And as we've heard, it takes the universe from when things were quantum fluctuations to quark soup and the production of dark matter and Big Bang nucleosynthesis and the formation of atoms and the growth of structure to the acceleration that we see today. And of course, this is the iconic picture of the microwave background taken by the WMAP satellite. Or no, maybe it was Planck. Okay, I think it was Planck. So they're surprised that it's still with us. And what I said yesterday is 6 numbers describe the universe. That's quite remarkable. Phone systems require many more numbers than that. And here is the temperature power spectrum, and here is the polarization power spectrum. And you can see that these 6 numbers produce a curve that does a very good job. And there's all these numbers. So from this, we're doing precision cosmology. There's the temperature to 4 significant figures. Let's see, I'm going to point to the Hubble constant. I want to come back to that. The age of the universe, which is out of date by 2 weeks. And Renata talked about the scalar index. And I'll come back to this, the number of light neutrino species. So that's quite remarkable. Here's some of the data. You can't even see this, how well lambda and matter fit, because the final circle is very tiny when you fold together supernova data and Planck data and baryon acoustic oscillation data. And inflation, Renata did a really nice job of saying this. We have a flat universe. It's almost scale invariant. Cold dark matter works pretty well. That's a matter of some discussion. No evidence for non-Gaussianity. So this is remarkable that this simple model works so well. A couple of other things that I wanted to point out that hadn't been pointed out, and this idea that we have non-baryonic dark matter. Often different pictures are put up, like the bullet, which probably tells you nothing about that. But it really hinges upon the determination of omega BH squared from the microwave background and from Big Bang nucleosynthesis. These 2 methods, one based upon gravity-driven acoustic oscillations and the other nuclear reactions when the universe is a second old. You get this number. And from the microwave background and large-scale structure, you get for omega m this number that's 50 sigma different. So it doesn't matter if it's 50 or 10. There's non-baryonic dark matter. Or there's something very wrong with the foundation of this model. And I can't help but saying how amazing this is that when we look at the sky, we're looking at quantum noise. And we're looking at galaxies when they were just quantum noise. Let me, I had to show this slide. So this model, yesterday's discussion, we talked about why are we unsatisfied with lambda CDM. I'll come to that in a second. But this picture would largely be an illustration of Steve Weinberg's book, where the term standard model was coined, not to refer to particle physics, but to refer to the hot Big Bang. So I think the hot Big Bang, although it's not as expansive and there wasn't as much data, it was a more satisfying model in the sense that all the physics in it was well-known physics. Nuclear physics, well, maybe it had the quark soup and maybe it didn't, but still that's known physics. The formation of the microwave background, gravity-driven structure formation. So that's in some ways a more satisfying model, a more satisfying theory than cold dark matter. Lambda CDM, as I continue to sing its praises, it's revealed new physics. And I'll come back to there's another way to look at that statement. So the repulsive gravity of dark energy explains the cosmic acceleration. An early burst of tremendous expansion called the cyclic universe explains, I was just checking to see if Andre was here, no, of inflation, explains our smooth flat universe with seeds for galaxies coming from quantum fluctuations, and the gravity of slowly moving dark matter particles holding all structures together. Okay, so here's I go in the other direction. Why is lambda CDM not good enough? Well, if we start at the bottom, it really is a model, not a theory. So it's a very good fit to the universe, but it's not a theory. Why isn't it a theory? Well, it explains dark energy with lambda, or I would say vacuum energy, and we can't calculate that. Or when we do, we get infinity. There's no standard model, let alone a fundamental model of inflation. And by the way, inflation might not even be right. Is that correct, Andre? Yes, okay. And what is the name of the dark matter particle? And more than one person has commented that this could just be an example of how nimble cosmologists are. Remember, it was Landau who said, you know, often in error, never in doubt, always entertaining. I don't know if he said the third part, but he said the first two. And so maybe we've just been inventing new things as fast as the observations have come along. But I'll just go back one slide. The other way to interpret this is that just like astronomers revealed the existence of helium, first found in the spectra of the sun, we're revealing new physics here. So what is the path forward in this era of precision cosmology? And I think it's the same as any time in precision science, is you can disrupt the current model by making a very careful measurement, or by making a very careful measurement, you can make discoveries. And so I'll just walk you through the H0, which I think is very important. It may not be a disruption. Maybe it's just systematic errors. A little bit about cosmic acceleration. Renata did such a good job on B modes. I'll go through that quickly. And I'll end with the larger mysteries ahead. And this should take no more than an hour. Oops. Uh-oh, what's that? Okay. So precision cosmology started out as a bumper sticker, but it's really hard. And so actually I made 3 bumper stickers, and the second one is precision cosmology is hard. So it's hard to make all of these measurements. I think everybody's coming away with a sense of that. And then the third one is accurate cosmology is even harder. And so everybody knows the difference between accuracy and precision? Okay, so you've seen the target with the darts and the, okay, good. So let me first talk about possible disruption. That's one way to getting a better model, and that's what I call the H0 portal. So we heard about this discrepancy. It's about a little more than 3 sigma in direct measurements. So those come from the distance ladder. And the ones that involve the microwave background and implicitly assume lambda CDM. So they're actually measuring something slightly different. And here is, as a function of time, precision increasing. We don't know that accuracy was increasing, but precision was increasing. And so we have a discrepancy. And this discrepancy, it could be that both methods, the methods that assume lambda CDM and the ones that really directly measure the expansion rate of the universe are both right, and the assumption of lambda CDM is wrong. That's one possibility. But in fairness, I should say that given the history of the distance scale, and we had a beautiful talk by Nick about how hard this is to do, it could be that there is just a systematic error there. And, well, Francois will tell us more about the microwave background, but it could be that there's a systematic error there and the two just coalesce, and the number of 3 sigma discrepancies that there have been, often they go away, although this one has been growing. And there could be discovery, and I think Francois said this yesterday, and I'll say it again today, is that there really is no good theoretical way, discovery that would reconcile these. You can do some things. You could change the equation of state of dark matter, but then you cause problems elsewhere. So, but this has the potential to disrupt if these two numbers truly are. And I just, because gravity waves are in the title of this meeting, we have a new way to measure, or we potentially have a new way to measure distances that was mentioned earlier, is that when we look at these coalescences of black holes, we get a distance. Unfortunately, we don't get a redshift. But if there's electromagnetic fireworks that go off with that, we have a new way of measuring distances. And so maybe that can help resolve it. Another disruption involves disrupting either lambda or general relativity. So let me just go forward here. If we try to measure the dark energy equation of state, as several people have mentioned, using these data sets, we get a number very close to -1. So it sure looks like it's lambda. So lambda has passed the static or the kinematic tests, but there's a new set of tests that probe things in a more dynamical way based upon the growth of structure. So this is the inhomogeneity on the 8 megaparsec scale, the famous sigma 8, as a function of redshift. And by cross-correlating microwave background and large-scale structure data, you can measure this. What's been done so far are these red error are the blue error bars, excuse me, and this is lambda CDM. And here's some other theory, and you can't distinguish between the two of those, so it's not general relativity, it's some other theory. And you should be able to shrink these error bars when the data from the dark energy survey, the 5-year data is in, and the better measurements from the microwave background. So this is a way to disrupt the current paradigm. Okay, and I already showed you that. There we go. So actually, I'm not going to talk about this very much. I hope I got the French. Did I get the French right, Francois? I'm not going to try to pronounce it. I'll leave that to Francois to pronounce. So another disruption is if you look very carefully at this fit and look at the residuals, la dent. And you'll talk about la dent, right? Yeah. So this, you know, these, you know, some of these points look like the normal kind of thing you would get if you, so is there something here that's trying to disrupt this? Let me go on to discovery. And the B modes are so important, and Renata did a great job of introducing them. I'll just say a couple of things here, mainly how hard it is to do. Renata said that, but this is the iconic B mode picture from Bicept, and they are indeed B modes, and they're beautiful, and you can see the odd parity, and you can see the swirling, but we now know that most of that, probably all, is due to dust. But there's another thing that you have to worry about. So here is a synthetic map of the sky with only E modes. And here is a tiny B mode signal in the nomenclature. R is 10 to the minus 2. And the temperature scale has been multiplied by 30 so you can even see it. Okay, so you have to detect that against this. And remember, it's multiplied by 30. But wait, it's harder, because the large-scale structure in the universe takes E modes and turns it into B modes. And so there are the phony B modes that are produced by large-scale structure. And so in order to get there, you have to de-lens. You have to take out the lensing. Okay, let's see. So probably all the non-astronomers learned that the bane of astronomy, if you sleep through any astronomy talk and want to ask an intelligent question at the end, just say, what would the effect of dust on your measurement be? And you'll stump the speaker, you'll look intelligent, and you'll have had a good nap. So this is kind of the state of play on BICEPT. So this is the joint analysis of BICEPT and Planck, a beautiful piece of work. And here is dust. So this is for the signal, the B-mode signal that was seen. This is gravity waves, and you can see that dust was clearly detected, and maybe there's something left over, maybe not. And here are the measurements of B-modes, but mainly what you're seeing is dust and lensing. And so here's the multiple moment. The one thing I want you to take away is we're doing nano-cosmology. This is 30 nanokelvin is the level of the signal. And this is an impressive plot because it goes from very low L all the way up to L of a few thousand. And the enemy up here is lensing, and, well, the enemy everywhere is dust. And so, this is a slide showing this was a first attempt to do de-lensing, and so far not very good. Well, I mean, it shows that you can do it, but this is what you actually measure, and these are the red are the de-lensed, so you can barely tell the difference. Okay, more discovery, dark matter, and Joe did a good job of this. He pointed out that this is a plot that he showed. These are all the existing experiments. There's experiments operating in these regions. He pointed out, I was going to call it headroom, or bottom room. There's not much room against the neutrino background, but there could be a detection. I don't think anyone's mentioned axions, but it could be axions. Or something more exotic. So, for example, in this low mass range here, that's not what you'd expect for a WIMP, but maybe a asymmetric dark matter or something more exotic. And of course, there could be a disruption, some of the things that Joe talked about. Let's see, on to the big questions. So one thing that this model certainly does not address is, Robbie, who ordered that? And so if you see the march of time here, starting from Democritus, we started with atoms, and then we added the microwave background, and then neutrinos, and then exotic dark matter, identified it as cold dark matter, massive neutrinos, so some of the dark matter is neutrinos, but it looks like most of it is cold dark matter, and then dark energy, and then another neutrino species. So first of all, do you really believe we're done? How much headroom is left? Well, on the ultra-relativistic particle side, I just made up this number, but maybe 20% of the microwave background, maybe slightly less than that, maybe 10%. On the non-relativistic side, I would have to have a debate with Joe Silk about this. How much dark matter could we put in something more exotic? But we have this dimensionless ratio of cold dark matter to baryons. That's 5. Well, it's not exactly 5, but so where did that number come from? And a fundamental theory ought to take a run at that. And of course, asymmetric dark matter would be a fantastic way of doing it, because if you imagine that the asymmetry in the dark matter and in the baryons are similar, then it's just measuring, roughly speaking, particle masses. So that's a big one. And I got to ask Andre about this. So we can't forget atoms. I think they're important for some reason. I can't remember why, but atoms are important, and we have to explain those. And baryogenesis. Andre, is it true that I thought that someone told me that the first time he presented this paper was on April 1st, and were you there, Andre, or? Do you know anyone who was there? Somebody told me that everyone thought it was a joke, that this paper was so far, because of course he talked about Probably most people didn't even appreciate the baryon asymmetry and talked about baryon number violation, CP violation existed there, and then explained how you could actually do this. And this may be tied to neutrinos, but this is a puzzle we have to solve. The multiverse. This gives me a headache. Because it could be the most important discovery since Copernicus, and that's where Andre stops reading on this slide. But is it science? Is it testable? It could be, you know, Nick had these big questions about the Big Bang, which, you know, of course is, it's the beginning of the universe. It's a singularity. It's something we don't understand, or before the Big Bang. And so this is certainly a very big question, and I think that's all I have. Oh, sorry, that's for another talk. That was for another audience. That's not for this audience. But we do have a president who's really devoted to science. Good, that's what I wanted to say.